Hello everyone. In this video I'm going to show you how to create a camera that scales automatically to a tileset and which also is able to scroll along it. In order to do so, we first need to see how this camera behavior would actually work. For that, we can make some drawings. So we have a few possibilities. For example, we could have a tile map which looked like this. So it's a rectangular tile map with the x-axis larger than the y-axis. In order to create a camera which zooms to this tile map, we would have to scale the camera down to the smallest axis. So we would basically have to scale the camera to the y-axis. And we would result in having a camera that would be looking like this. Now, obviously, if we wanted, we could scroll this camera left and right in order to cover the full tile map. Another thing we could do, in the case in which we would have a vertical tile map with the x-axis shorter than the y-axis, then we would again scale the camera to the smallest axis, which is this time the x-axis. So our camera would be scaled like this. Having the camera scale like this, then it would be able to scroll up and down. And one final case would be a case in which we have a tile map which relative to the camera, let's say this is the camera, is very, very big. Now in this case, maybe we do not want to scale the camera too much because we would lose some pixel details. So we could apply a limit to the scaling, and let's say we could scale the camera to only this size. And if we have a camera of this scale, then we would be able to move it to the right, to the bottom, or even move it diagonally in order to be able to cover the whole tile map. Now that we know this, let's create a script for the camera 2D in order to replicate this behavior. I'm going to click on Attach New Script and leave everything as default and click on Create. Well, the first thing we need is the actual tile map because our camera has to scale to that tile map. So I'm going to write it down here. var tile map, which is of type tile map. Okay, this is going to be exported in order to be able to simply assign it here. We can even assign it right now. We can see that we have this variable here already, and we assign this tile map here. Okay, now that we exported this tile map, we can go to our ready function. So when we start our game, we would like to have the camera automatically scaled to the tile map size. If we run the game right now, we see that we have a few problems. The first problem is that the left corner of our camera is not in the same position as the left corner of our tile map. That is going to be an easy fix because the camera has a property which is called anchor mode. This anchor mode can be set to drag center or set to fix top left. And what it does is basically it changes this anchor to not be inside the camera in the center, but to be at the top left corner. So if I set here the anchor to be fixed top left, we see that the camera is now anchored to the top left corner. We can change it here, or if we want to make sure that it is always going to be changed, we can write down here set anchor mode and autocomplete to anchor mode fixed top left. Now, if we run the game, we can see that the camera is anchored to the top left corner, which is exactly what we want. Now, the problem that we have is that the camera is not zoomed into this region. For that, the camera has a set zoom function. So if we write set zoom, we can give in a vector2, and this vector2 can take two values, which if they are greater than 1, the camera is going to zoom in, and if they are less than 1, the camera is going to zoom out. So let's see a few examples. If I give 0.5 and 0.5, the camera zoomed out, and now we can see even more of everything. If, for example, I give 1.5 and again 1.5, the camera zooms in, and now we see a lot more details of the pixels in our tile map. Now, what we have to do is to find this value that we have to use for our zoom vector. So let's try to find that. Let's make a variable var zoom vector. And let's call a function which gives us the zoom vector. So I'm going to simply call something like, I don't know, get camera zoom to tilemap. Yeah, let's call it like this. Now, if I go here, I can create func get camera zoom to tilemap with no parameters. And let's see how we are going to accomplish this. Now, in order to get the zoom vector, we need to know the ratio between our viewport, which is how much we can actually see on the screen, and the whole tile map. Let's see how that would work. So, for example, in this case, our tile map is longer on the x-axis than the viewport. So basically, the ratio of our tile map is going to equal, if this segment is A until here, and this segment is B, then it's going to equal A plus B divided by Y, while the ratio of the viewport is going to simply equal to A divided by Y. Now, obviously, this ratio is larger, so RT is larger than RV. We see that in this case, we are going to scale to Y. In the other case, if, for example, this segment is A and this segment is B, we see that the ratio for our tile map is equal to what? It's equal to X divided by A plus B, while the ratio for our viewport is equal to X divided by A. In this case, it's obvious that RT is going to be smaller than RV. So when we have the ratio of our tile map be equal to less than the ratio of our viewport, we are going to scale towards the x-axis. Okay, knowing this, I think we can move on to implementing our zoom function. Let's get back to Godot. Let's look at our script and see what we can do. Well, first of all, we would like to actually know what the size of the tile map is and to actually know what the size of the viewport is. Now, to get the size of the viewport, we are simply going to write what viewport size equals to get viewport dot size. This is going to return an array with the x and the y sizes for our viewport. And on the other hand, we have the tile map object here, which we can use to get the size of a tile and to get the number of tiles on each axis. Let's see how we do that. Let's declare a var tile map info maybe, which is equal to get tile map info. And this is a function that we are going to define. So let's have here func get tile map info, and let's see how we work with this. Well, we can say var tile size equals to what? Well, a tile map has a tile set, so we can say tile map dot get tile set, and this tile set has a predefined tile size, so we can say dot tile size, and we have found this size for a tile. Now, we also need to know how many of these little tiles we have. So there is another function, which is, I'm going to put it in a variable, tilemap rectangle is going to be equal to tilemap dot get used rect. This is basically going to give us the used area in our tile map and basically tell us how many of these tiles we have horizontally and vertically. Now, with this information, we can actually build our tile map size. So let's just say that var tile map size is equal to vector 2i, because it's tilemap, it's going to be at multiples of integer values. And let's just say that the x size is going to be tilemap rect.end.x minus tilemap rect.position.x, and on the y-axis we're gonna have tilemap rect.end.y minus tilemap rect.position.y. Why are we calculating it like this? Because tilemap rect end.x is basically telling us that, okay, the tilemap on the x-axis ends at this position, and we have also this tilemap rect position x, basically telling us that it starts at this position. So by making a difference between this one and this one, we are going to find the size on the x-axis. And by making a difference between this one and this one, we are finding the size on the y. Now that we have these, we can simply return them. And let's return them like this. Return size, which is tilemap size, and also tile size, which is going to be tile size. Now that we have this information, we can simply calculate the whole level size. So we are going to say var level size, which is going to equal to a vector to I of what? Of tilemap info dot tile size multiplied by tilemap info dot size. We are basically saying, okay, for each of the tiles in the tile set, multiply that value by our tile size, which in our case is going to be 32, if I remember well. Yeah, it's for us, it's 32 pixels. Okay, now that we have these informations, we need to know the aspect ratios. So for the viewport, let's make another variable. Viewport aspect, maybe let's call it simply like that. And this aspect ratio is going to be the viewport x divided by the viewport y. Well, the viewport x is viewport size 0 divided by viewport size 1. This get viewport size returns an array, so it's going to return something like this. And the first value is going to be x, and the second value is going to be y. Now, another thing also, these values are going to be integers, so let's cast these to a float. And we basically have the viewport aspect ratio. Now we can do the level aspect. And this is going to equal the same, meaning that it's going to be level size dot x divided by level size dot y. And also let's make this level size dot x a float, so that we are dividing float numbers instead of integer numbers. Okay, what we have to do now is to check if the level aspect is larger than the viewport aspect, and in that case we scale to y, otherwise we are going to scale to x. So if level aspect is larger than viewport aspect, we can simply divide by the y-axis. So let's define a zoom level. Let's call it new zoom. And let's initialize it with 1.0. And this new zoom value is going to equal the viewport size on the y-axis. So viewport size on the y-axis divided by the level size on the y-axis. Make this a float in order to not divide again two integers, and otherwise we are going to divide by the x-axis. I'm not going to write this again. I'm just going to copy it. And here we take the viewport size on the x-axis, and here the level size again on the x-axis. Nice. Now we have pretty much everything. We have the zoom level, so we can simply return vector2 of new zoom and new zoom. Now that we have this value, we got the camera zoom to the tile map. We can apply this zoom, so we can simply call set zoom on our camera and give the parameter this zoom vector. If we save, everything should be in order. If I press F5, we see that currently everything is scaled to the tile map. Now what's left to do is to be able to move on this tile map. If we want to move, we have to go to our process function and get some input from the player. So in order to get some input, we have to first define it. We can go to project settings and let's go to input map and let's add some new actions. I think we could call them camera move up. Let's add one, camera move down, camera move left, and camera move right. And I'm going to press on the plus button here at the camera move up. And I want to move on the WASD keys. So for moving up, I'm going to press W and press OK. For move down, I'm going to press S, press OK. For left, press A, press OK. And for right, press D and OK. And everything should be set up. And now if we want to actually get that input vector, we are going to say var input vector, which is equal to input dot get vector. And let's have here, let's maybe look at the parameters first. So get vector, it's going to request the negative x, the positive x, the negative y, and the positive y. Okay, so then the negative x should be left. So let's say camera move left. The positive x is going to be move right. The negative y is going to be move up, and negative and the positive y is going to be moved down. Okay, now that we got our input, we need to calculate a velocity vector for our camera. Let's define it here. So let's say var velocity, which is going to be a vector 2. And let's initialize it to vector 2.0. And also maybe we want to have an acceleration to this velocity. So let's define var camera, maybe let's just call it. So let's define it, var acceleration, which equals, I don't know, something like 100. Having these, we can simply go and create a function called calculate velocity of input vector. Okay, let's see how this function would look like. Well, func calculate velocity, and let's maybe call this direction to be more clear what we want to do with this. And in order to not make it dependent on the process, maybe we want to calculate it somewhere else. I'm going to find the delta here. So I'm just going to say var delta equals to get delta, get process delta time. And this is basically going to get me the delta as if I would have passed it down from the process as a parameter. Now what I want to do is simply say velocity plus equals to what? To the direction vector multiplied by acceleration multiplied by our delta. Also, we would like to be able to stop our camera at some point. So let's create a var release falloff variable, which is going to be something like 35. Why not? Let's try this value out. And we are going to basically apply this release falloff to our velocity using the improved lerp function. In the rest of this tutorial, you are going to see me using the lerp function a bit different than you would expect. So for example, The lerp function would be used with a source, a target, and finally a rate. And I will be using it like this, with a target first, then a source, and then 2 to the power of minus rate times delta. Why am I using this? Well, first of all, I am using the delta because it makes it frame rate independent. And second of all, the graphs of these functions are basically, so for this linear interpolation that has, let's say, a rate of 0.1, there would be a linear graph, and for this other interpolation, there would be an inverse exponential graph. So basically, it would go on like this. So this highest value, which is the value which we want to get, would be actually the first one, and the lowest value would be the second one. You don't really have to care about this too much if you want to use the lerp normally with S, T, and R times delta. It is perfectly fine, and it shouldn't affect how you move on with this video. So let's see. If, for example, we are no longer pressing A or D, so if direction.x equals to 0, then we are simply going to set the velocity.x to be equal to lerp between what? Between 0.0 with velocity x. We could obviously also go with velocity.x equals to lerp between the actual velocity to 0.0 and to have something like all of multiplied by delta. And this would also be fine, but this is going to give us a much better result visually. But this is going to give us a much better result. Okay, we can also apply this for the y-axis. So we can say direction.y equals 0. So basically, if we're not pressing W or S, we are also going to slow down the y-axis. One final thing that we could do is to also clamp this velocity to not make it accelerate forever. So let's define a max speed. Let's say var max speed, and let's make it 20 or something, doesn't really matter. We'll see how it looks and how it feels. If we don't like it, we can change it. And we can simply say velocity.x equals to clamp. And what do we want to clamp? We want to clamp this velocity.x between minus maximum speed and plus maximum speed. And we want to do the same for velocity.y. Now all that's left to do is to simply update our global position based on this calculated velocity. So let's make another function here. Let's call it update global position. And in the same way, we create a function. And we can say global position equals to what? Well, we don't want the global position to equal a value directly. We want it to get to that value gradually. So let's just say it's plus equal lerp. And again, we are going to lerp between what? Between the vector velocity and between vector 2.0. So we want to go from vector 2.0 to the velocity vector. So if we apply the improved lerp function, then we are going to say velocity first. And afterwards, we are going to say vector 2.0. And we will go with a rate of, I don't know, power of 2. And here again, some kind of fall off. Let's make this 32 multiplied by delta. And having that, we, I didn't write properly, global position. Okay, and delta is not declared in the current scope because I did not define it. Maybe let's just add it to this variable delta equals to get process delta time. And now we basically change the global position. Let's see how this happens. So if I press F5, something weird is going on. I'm only able to move diagonally. Let's see where the problem is. Oh, I just noticed that I have clamped the velocity.y to velocity.x. So if we modify it here, then it's going to work properly. And yes, if I move with WASD, it's moving quite smoothly. But we see that we have a problem. The problem is that, yeah, we are getting out of our tilemap area. So how do we fix this? Well, there is another useful concept called camera limit. We basically can set a camera limit which does not allow the camera to move more than the set limit. So let's just do that. So when the camera is ready, after we zoom in, we can basically just say, let's make a function, apply camera limits. And with this function, we can basically tell our program that we want our camera to only move between certain boundaries. So let's say apply camera limits. So define it, func apply camera limits. And here we need to know where the camera can go. Well, the camera is supposed to only go somewhere inside this tilemap. So the limits should be actually defined by the tilemap. If we go back to the script, we see that we obtain the tilemap info and level size with these lines of code. So I'm just going to copy and paste them here. And now that we have this level size, I'm simply going to create the limits based on that. So I'm simply going to say set limit and specify the side on which I want to set the limit. Now, the left and the top side are going to be 0. They are going to be 0 because this top left corner is in 0, 0. So that is going to be pretty simple. So let's go with side left, and we set this limit to be 0. Set limit side top. This is going to be also 0. And now let's think about the limits on the right side and on the bottom side. Well, we basically just need to know how big the level is on the x-axis and how big it is on the y-axis. So we are simply going to set the limit to the right side right to be equal to level size dot x and set limit to the bottom side, and let's make it level size dot y. Now, if we run our program, we are going to see that we are no longer able to move anywhere else other than on the tilemap. But though, there is still a problem. It's not very noticeable if you watch it on video, but if you go too much to the right, if you want to come back to the left, you will see that it sticks there for a little and only afterwards it comes back. Now, why does this happen? Let's see in the scene view why this might happen. I'm going to hide the tilemap for now, and let's click on the camera 2D, and let's pretend that we have some already set limits. So I'm going to set the left and top limit to be 0. Let's make this something like 2000 and the other limit, I don't know, 1000. It doesn't matter too much. Okay, I do not see anything right now, but if I check draw limits, I start seeing the limits. Okay, now what these limits do is that no matter where the position of the camera is, the viewport is going to stay between these limits. So if, for example, I drag my camera, you can see that it goes along with the viewport. But if the viewport reaches this margin, then it is going to stop. But the position of the camera does not stop. As you can see, I drag the camera until here. So in our example, if I keep pressing right after we reach the edge, the camera is still going right. And it's still going to go right until we press left again. And that's why when we press left, nothing happens for a while, because the camera has to get back in this position and move the viewport left once it reaches the top left corner. In order to avoid that, we also need to calculate some limits for movement and not let this camera move more than what? More than the size of our tile map minus this scaled viewport. So let's see how we achieve that. Undo. Let's go back to our script. And let's look a little in our update global position function. So in our update global position function, as I said, we need to calculate the zoomed viewport size, and let's put it in a variable. So var zoomed viewport size equals to get viewport to zoom scale. Okay, and this get viewport to zoom scale is going to do a few things. It's basically just going to check on the zoom vector. So var zoom vector, which equals to get zoom. And it's going to divide this viewport based on how much we zoomed in or out. So we are basically going to say var zoomed viewport size equals to vector to I, and the x is going to be equal to get viewport dot size, and we are taking the first element from that array and divide it by zoom vector dot x, and we are going to do the same for the y. So get viewport size and the element on the index 1 of the array divided by zoom vector dot y. Finally, let's just simply return zoomed viewport size, and we now have the size of the zoomed viewport. We can move on and simply clamp this global position value to the newly defined limits. And what are the limits? Well, the first limit is going to be the left limit. So the left limit is going to be equal to get limit of side left. Okay, the right limit. This one is going to be equal to get limit of side right. But as you could see before, this anchor, even if the viewport reached the limit, could still move. So we have to go with this anchor exactly until the viewport reaches the limit. So basically, we're not going with the anchor to the right side, we are going with the anchor to the right side minus the viewport. So we are going to subtract from this zoomed viewport size.x. Now let's repeat the same thing for the other ones. So let's have here a top limit, which is going to be side top. And let's have here the bottom limit, which is going again to be side bottom. But we take into account the viewport height. So basically viewport size.y. And now that we have this limit set, we only have to clamp the global position. So let's go and say global position dot x equals to clamp. What do we want to clamp? Well, we want to clamp global position dot x between the left limit and the right limit. And we want to do the same for y, but we want to clamp global position dot y between the top limit and the bottom limit. Now, if I save this, it's going to take me to the right, and I keep pressing D. And when I press A, it instantly gets me back, and I keep pressing A. And when I press D again, it instantly gets me back. So we no longer have to wait for the camera to get back from that imaginary position after the viewport. Okay, this is basically it. What's nice is that it works for all kinds of sizes. So for example, if I went to this tile map and let's say created even more grass, it would automatically scale to that grass size. So it's scaled vertically, and now I can scroll down, or I could even remove some of it. So let's say something like this and something like, I don't know, something like this. Let's not cut the poor trees. And now it is much smaller and maybe even prettier because we are much closer to the actual pixel sizes. One other thing that we can do is not only change the aspect ratio of this image, but we can also change the aspect ratio of our viewport. So for example, if somebody is playing your game vertically, you can go to project settings and let's just pretend that we have a vertical monitor here. Let's say it's 500 by 180. And if we save that, now we can press F5. And even though we have a vertical monitor, everything has been scaled to this screen. And we can basically move along this. The only thing left to do would be that limit to the camera if the tile map is too big, but that is going to be pretty easy to set up because we can simply go to our zoom function, so get camera zoom to tile map, and if we want, we can clamp this zoom value and we can say something like new zoom equals to clamp of new zoom, and the minimum value could be, let's say, 0, and the maximum value could be 1.5, why not? And now if we go to our tile map, we see that it no longer zooms more because probably already our zoom is larger than 1.5. So if we print it here, our zoom is 2 already, so it only lets the zoom work up until 1.5. Okay, but this has been pretty much it. Thanks a lot for watching. I will be adding this script to my repository, which I will leave in the description, so you don't have to copy it manually from the video. Hope I helped you, hope you learned some things, and see you in the next one. Thanks a lot. Bye.